the canonical use of deadlines in lingua franca is for situations like this, where you've got a sensor that is either driven sporadically using a physical or logical action, or triggered periodically using a timer. And then you have a reaction that reads the sensor data, produces it, you do some processing, and then you have an actuator, and you want to specify an end-to-end deadline. And so the intent here is that when you specify in the actuator a deadline, which in this case is specified using a parameter, the limit, okay, which defaults in this example to 50 milliseconds. The reason that this is specifying an end-to-end deadline is that the semantics of the deadline is that if the physical time at which this reaction is to be invoked is less than the logical time plus the limit, okay, then the normal reaction will be invoked. The deadline is met. Okay, if on the other hand, the physical time is later than the logical time plus the limit, then the deadline body will be invoked. So this is meant to be an exception handler handling a deadline miss. Okay. So first of all, in case anyone doesn't know our terminology, we define the lag to be the difference between the physical time and the logical time. Okay, so the deadline is always the number of the deadline is always checked against the lag. So when the reaction is about to be invoked, you check the lag. The runtime system checks the lag. If the lag exceeds the limit, then it invokes the deadline handler, the exception handler, instead of the regular body. Okay, so that's a straightforward thing, and we have a little test case here where the processor takes some amount of time that is a parameter. Okay, so it does that using this sleep function, right? So the exact time is specified as a parameter here that that defaults to 10 milliseconds. Interesting. This should have a, shouldn't this have a type? Okay. So if I run this, you'll see that in fact, the deadlines are all met. So if I look at the actuator, it prints out met deadline if it meets the deadline, and otherwise it prints missed deadline. So if I increase the exact time to say 60 milliseconds and run it again, then it'll miss all the deadlines. Okay, totally straightforward. Now, one thing that often puzzles people, and that which I would like to explain and defend, right, is that the deadline is checked at the start of a reaction. Okay, so the reaction will, the physical time gets checked before the reaction gets executed, and the deadline is deemed to be missed if the reaction is going to start too late. Many people seem to want the deadline to specify a constraint on when the reaction ends. Okay, now why don't we do that? Why do we do it on the start? Well, if you wanted to do it on the end, the logical place to put the deadline would be at the end of the processing, right? Because really, that's, I think, where the potential problem here is. The processing is taking too long. Okay, but the problem here is that then if the actuator has no indication of a deadline, there's nothing to tell the runtime system that once the processor ends, it should immediately invoke the actuator. So once the processing ends, if it could meet the deadline, and then if you have a bunch of other stuff in your program, the runtime system may go ahead and invoke a whole bunch of other reactions before it invokes the actuator. So that would be pretty undesirable, right? And you wouldn't you wouldn't actually have actuated on time, which is really what you want to be doing. The second reason is that you don't really want to execute the body of this reaction only to then discover after that that you missed the deadline, right? Because you've already actuated now in the physical world based on potentially stale data, and that might have been a real error. You might have launched a missile, right? And you shouldn't have launched the missile if you missed the deadline. So you can't then invoke the exception handler and unlaunch the missile, right? That doesn't really make any sense. So the deadline really needs to be checked at the start of the reaction so that you can have a body of code that you cannot execute in the event of a deadline miss, right? So, yeah. So then the other thing that the runtime system can do is, because the structure of the program is statically analyzable, the fact that this actuator reaction has a deadline and depends on these other two upstream reactions means that the runtime system can go ahead and prioritize these upstream reactions based on the downstream deadline, right? Because that dependence information is available to the runtime system and to the compiler for that matter. Okay. Okay, so those are kind of the key reasons why deadline is associated with the start of a reaction, and the check gets done at the start of the reaction. Now, let's look at another example. This one is a scenario where, okay, maybe you really do want to check to see if a reaction has ended on time. Okay. Despite everything I just said about why you don't want to do that, perhaps you have a good reason. Okay. Maybe it's a health check, right? You're doing a health check on some operation, and you want to make sure that this reaction actually did complete on time. Well, there's a very simple pattern for doing that, which is to just simply specify a second reaction in the same reactor with a deadline. Okay, now the semantics of lingua franca is that any two reactions in the same reactor are mutually exclusive. Okay, so they can't execute concurrently. They will execute in sequence. And moreover, they execute in the sequence in which they're declared. Okay, so reaction one will always be executed before reaction two. And consequently, you can use reaction two to check whether reaction one ended on time. Now, once again, you have the issue that reaction one could end on time, but your runtime system may have other reactions elsewhere in the system that are enabled. And so it might execute those before it executes reaction two. And then reaction two might erroneously think that reaction one did not end on time, right? Well, there's a very simple fix for that, which is actually currently a work in progress in Lingua Franca. This is actually something that Francesco has been working on that we hope will become just a routine part of the runtime system, which is that when a worker thread picks up a reaction, its priority gets set on the basis of the current difference between the lag and the deadline. Okay, so the closer it is to the deadline, the higher the priority of the worker thread will become. So as a consequence, if reaction one finishes very close to the deadline, reaction two will have a very high priority. Okay, and consequently is very likely to be the next thing that the runtime system will execute. And it will only not execute reaction two if there is something else in the system that actually has a higher priority that is closer to the deadline. Okay, so that mechanism by itself will tend to ensure that reaction two will execute right after reaction one, unless reaction one really ended, finished way early, in which case this won't have such a high priority and it won't really matter. because it doesn't need to check very quickly.
Edward, I have one question.
Hmm.
Uh, could you give us an example where this reaction 2 in check reactor gets prioritized over other things to be done by the runtime? For now, I think it's natural to guess that, oh, that's the next reaction in check, so it should be executed next anyway.
Actually, the C runtime has an optimization where it will chain, when it has a chain of reactions with
Mhm.
a simple dependency like this and no other dependencies, it'll go ahead and execute reaction two immediately without
Mhm.
even going through any runtime decision making. But in principle, if I had, for example, a second check, okay, let's just create another instance of this. And that was wired up like this,
Mhm.
then it's quite possible that if you have only a single core, right, maybe
Mhm.
let's say this second check has um, a limit of 100 milliseconds, right? So it has a lower priority, or let's make it even closer, 55 milliseconds. All right, so what could happen on a single core is that the core would execute this reaction, then this reaction,
Mhm.
okay,
Mhm.
um, and then this one, and then this one, right?
Got it. Got it.
But this earliest deadline first schema would prevent that, okay, because this reaction here will have an earlier deadline than either of these.
Uh-huh.
Okay, so if you have the worker thread appropriately set the priorities, you will ensure that reaction two will execute immediately after the
Got
check.
it. So is it correct if I understand this as a sort of EDF, but respecting the dependency graph?
Yes,
Got it. Got it. Okay. Thank you.
yeah, this is EDF with dependencies precisely.
Got it.
Yeah. Um, so again, I want to emphasize that there is an attempt that I'll talk about in a minute in the C runtime to implement EDF, but it actually falls far short. Right. So the work that Francesco is doing is a much more rigorous implementation that um, we expect will become a routine part of. He's actually doing the work in Reactor Micro C, although well, he's done some work in both, right? Reactor C and Reactor Micro C. But the current emphasis is getting this rigorous EDF working in Reactor Micro C first. Um, Okay, let me now talk about some of the subtleties that arise. All right, so let's look at a slightly different model, but a related one. Okay, so this one is one where we have the sensor processor actuator chain, but it's replicated. Okay, there's another sensor processor actuator. So you're driving two different actuators on the basis of the same sensor data. And in this case, suppose that this processor has an execution time of 60 milliseconds. Okay. Um, so I guess that must be the default in the actuator. Um, where is this? Oh, here's where it's instantiated. No, this is where the execution time of 60 milliseconds is specified. Okay. So um, this has an execution time of 60 milliseconds. This has a deadline of 50 milliseconds. So the deadline's always going to be missed. All right. But the one below has an execution time of 10 milliseconds and a deadline of 50 milliseconds. So you might expect that the deadline would be met. All right. But that's not actually what happens in Lingua Franca. So if I run this program, okay, I see that actually the deadline was missed on both every time. Anybody want to conjecture about what the reason for that is?
I would guess this is the result of doing level-based scheduling,
Right,
where P1 and P2 are at the same level. So there's a level synchronization here. We don't go ahead and execute A1 and A2 until both P1 and P2 finish.
right. So there's a scheduling strategy that's implemented in actually all of the current runtimes that Lingua Franca has that is a simplification. So in general, the scheduling problem is you get an event from the timer. Okay, there are going to be 5 reactions potentially that are going to be activated by that event. They have a dependency relationship. That dependency relationship is in general representable with a directed acyclic graph. It's an arbitrarily large graph. The runtime system could actually include a complete representation of that graph, and the scheduler could walk through that graph and look at the dependencies and make scheduling decisions. But that's not what our runtime systems do. They do a much, much simpler strategy, which is called level scheduling, which is that the graph gets statically analyzed at code generation time, and each reaction gets assigned a level, which is its distance to the root of the graph. So this reaction will have level 0. These 2 reactions will have level 1, and these 2 reactions will have level 2. And then the runtime scheduler uses a very simple policy that doesn't involve walking through a directed acyclic precedence graph. It just says, well, I have to execute all reactions with level 1 before I can execute any reaction with level 2, and that guarantees that all the precedences will be satisfied. Um, Unfortunately, in this case, that results in the deadline check occurring late, right? Because what's going to happen is that both reactions must execute before either of these 2 reactions executes. Okay, we made an early attempt to get around this problem, which I'll talk about in a few minutes, but it was actually a pretty abysmal failure. All right, so I'm going to show you um, what the current mechanism is to get around this problem. All right, so the most simple thing to do is, let me see, which of these is it? Yeah, this one. Oops, let's put this in the right screen. Okay, so the simplest solution is to use federated execution. Okay, so what federated execution will do now is when you create the top level reactor, you use this federated keyword, okay? And each of the 3 top level reactors that get created um, will get code generated into a separate program. And these programs now will have their very own scheduler with their very own static analysis. Okay, so and then a coordination mechanism is handled between federates, which in this case will be a rather simple coordination mechanism. So now um, the level scheduling gets separated so that this processor actuator chain will have its own level scheduling schema, and this one will have its own independent level scheduling schema, each implemented in a separate process. So now if I execute this program, it's actually going to generate 3 separate programs plus the coordination, and then execute that. And you'll find that on the execution, if we look at the outputs, you get missed deadlines only from um, the instance that has the excessive execution time. The one that has the lower execution time will meet all the deadlines. Okay. So that scheme decouples these scheduling the scheduling mechanisms, and therefore breaks the bottleneck due to the level scheduling. Now, we don't really need to create 3 of these. Okay. So let's see, we could get away with 2. All right, put a full sensor processor actuator chain in one federate, and then the processor actuator chain in the second federate. Okay. And if we code generate this and run it, we'll find the same thing, that the deadlines will be met in the one that has a smaller execution time. So if we look at it, yeah, here we get met deadline and missed deadline on 2 different federates, right? But you consistently meet the deadlines on the one with the smaller execution time. But you have to be a little bit careful here, okay? And let me show you how the code generator works for federated execution. So the first thing that the code generator does when you give it a federated program like this is that it actually splits this into 2 lingua franca programs, one for this federate and one for this federate. Okay, so let's look at the program that gets generated for the one on the left, the sensor processor actuator chain. So that'll get code generated into this fedgen directory. And let's find it. That's this one, SPA. Okay. Whoops. Put it in the appropriate screen. Okay. So this is a code generated lingua franca program. And one of the things the code generator does is generate this network sender reactor. Okay, so this is part of the coordination mechanism that gets produced. And so this is now a standalone lingua franca program that will execute this original composite reactor and then have this network sender to forward the sensor data to the next reactor. But this network sender is going to be subject to the level scheduling. Okay, so in this case, the network sender will have the same level as the processor. And now, if you have only a single core, and if you don't have any deadlines or the deadlines are the same, there's no basis on which the runtime system should choose between executing these 2, the processor or the network sender. So there's a risk that it will execute the long-running processor before the network sender, in which case you're going to end up missing both deadlines anyway, because the network sender is going to get delayed, and so the message to the destination gets delayed. All right, so that's
in Edward, in React Micros, we actually do this at the end of the tag. So basically, the sensor processor actuator would process basically, because we basically need to make sure that we actually send the last value on the port. So if basically multiple reactions, for example, write to one port, we basically do this now at the end of the tag as cleanup. We actually didn't send only at the end, we basically send this value. So for example, in Reactor Micro-C, this probably also would lead to a deadline violation.
Oh, interesting.
Just based on the fact that, you could, for example, now have a second reaction, for example, in the sensor that also writes to that port. And then we would both could basically write the port. So we basically also need to make sure that every reaction has execute and potentially written a value.
Very interesting. So I think that, one way to interpret that observation is that that's a downside of the approach that Reactor Micro-C is taking. Whereas in Reactor C, the network sender reactor, the fact that we produce a network sender reactor prevents that problem, right? Because
Yes.
as soon as the dependencies are satisfied for this reaction, it can just execute, right? And
Yep.
if there are multiple writers, then that will delay the activation, but it'll only delay it until all of the drivers have been updated. Modulo still having the potential problem of the level scheduling interface, right?
No, but that's, I would say, clearly one of the upsides of doing it this way, basically in generating LF components, is that you basically, if you have real-time scheduling, then also your networking will be subject to this real-time scheduling, which I think is one of the like one of the upsides of doing of a problem of this way, right? But this is basically
Yeah.
for us is a utility of the runtime.
Yes, very, very, very interesting observation. We need to think about that and maybe try to understand the implications and see if there's a way to work around that limitation in
Yeah.
reactor micro-C. Yeah, very interesting.
I'm just saying the difference here. Just
Yeah.
highlighting it.
No, it's a very, very good observation, and I was not that had not occurred to me. I like the way reactor micro-C handles the sending because it really is simpler than splicing in a reactor. But I didn't realize that it had this cost. Okay, yeah, very interesting. So, okay, so subtleties, these exist, all right. But let me raise another issue around deadlines, right? Which is that we go back to one of these, you know, the if we look at any of these reactions, right, that have a deadline, the fact is that because the deadline is checked when the reaction is about to be invoked, um, that could be problematic as well, right? Because, suppose that this processor has gone into an infinite loop, for example, then your deadline violation handler is never going to be invoked, right? Because you're never going to get to the point where this reaction is enabled, and therefore you will never detect the deadline violation, even though you've obviously had a deadline violation, right? So a key question is, can you in fact detect a deadline violation earlier? So for quite some time, we've had a mechanism that does that. And here's an example that's in the playground. This is a program called Anytime Prime, and it implements a computation strategy that is sometimes called anytime computation. And the prime function here, what it does is it is given a deadline, which in this case is just fixed at 3 seconds. Okay. In reaction to startup, this reaction is going to be invoked, and it has a deadline of 3 seconds. Well, this deadline is never going to be violated, right? Because there's nothing else to do in this program. So why specify a deadline at all here? Well, what this the body of this reaction does is simply iterate until this deadline would be violated, okay? And it calculates prime numbers until it runs out of time. So if I run this program, all right, what it's going to do is run for 3 seconds and then report the largest prime number that it was able to find within 3 seconds. Okay? So that is a mechanism that you can use in a reaction body to limit the execution time of a reaction body. So this is sometimes called cooperative multitasking, right? Where a piece of code will essentially suspend itself when it's overusing its budget. But this is not very modular and not very robust, right? Because it's not going to check a rogue reaction or a reaction that's somehow gone awry, and it only works for something that is cooperative. Okay, so here we can use a very nice technique, which is to use the decentralized coordination in federated execution. Okay, so here's the pattern, right? We've got our sensor processor actuator chain, and what we want to do is invoke some action when we realize that the actuator is not going to be invoked on time. And we want to do this as early as possible. Okay, so the way we can do this is by creating a federated watchdog is the term that I used. Okay, so this is the monitor federate. So the monitor federate has a timer just like the timer in the sensor. Okay, so it's going to be executed at the same, it's going to trigger at the same logical times and very close to the same physical times because there's every effort to execute it at the same physical time. The monitor reaction then will be invoked when either there is an input from the processor or the timer triggers. Okay, one or the other. So the other key parameter here is that the monitor has this safe to advance parameter, which is a property of the decentralized coordinator. And what does this mean? Well, in this monitor, there's going to always be an event available from the timer. You know, first at time 0, then at time 200 milliseconds, then at time 400 milliseconds. Okay. So the question is, when can the reaction be invoked? Well, according to Lingua Franca semantics, events should always be processed in timestamp order. So the reaction should not be invoked until you know that you've received all events on the input port up to and including the timestamp. Okay, so according to the semantics of Lingua Franca, because these two timers both have offsets of 0, they're both going to produce events at time 0. So there's going to be an event on the output at time 0. All right, but it's going to be physically delayed by whatever processing time is involved. Okay, but there will be an event at time 0. So it would violate Lingua Franca semantics to invoke this reaction early before receiving the event with timestamp 0. Okay. The default coordinator in Lingua Franca will simply delay invocation of this reaction until it knows that it's received all the inputs with timestamp 0. But that's not going to help us because if the processor executes for a very long time, then the coordinator, the RTI, will simply block execution of the downstream reaction until the processor completes. And so we won't accomplish the objective of early deadline detection. But the decentralized coordinator doesn't work that way, right? The way the decentralized coordinator works is that it doesn't consult the RTI. It just consults its local safe to advance parameter. And the safe to advance parameter is set to 50 milliseconds in this case. And so what will happen is, given the event with timestamp 0 here, the runtime system for this federate watches its local clock. And when its local clock hits 0 plus 50 milliseconds, it assumes that the input is absent and proceeds to execute the reaction. Okay? So what should the reaction do? Well, if the input is not present, that's a fault condition. Okay? So it has effectively checked that the processor, it now knows that the processor took more than 50 milliseconds to execute. The actuator is not going to get invoked in time, and it can therefore take action accordingly and handle the situation. So this particular program is configured so that the processor takes 60 milliseconds, and so if we run this, we'll find that the exception handler now, which is this ordinary reaction, will get invoked every time. Okay, so you can see failed to receive input on time at logical time 1000, also 800,000, 600,000. Okay, So that's a way to use the decentralized coordinator to handle federated execution, to handle, this early detection uh, of potential deadline violations.
Edward, I have one question and one comment.
Yeah.
Yeah, I might have missed something, but can we do the same thing, early deadline detection using scheduling enclave on the same non-federated
Yeah.
okay. Got it.
Yes, we can. So let me first, in fact, that was going to be the next topic I was going to talk
Oh,
about.
I see, I see.
Let me point out that everything that I have talked about here
Uh-huh.
is in this blog post. If you go to the Lingua Franca website, lflang.org, there's this blog key, and there's this working with deadlines blog. Okay. And that has everything I've talked about so far, including all the examples. And these examples are actually checked into the website repo along with the blog. Okay. And so the one I just showed is right here with the source code given. All right. But then it starts to talk about ongoing research, things that we've been doing, right? One of the things that we've been doing is actually there's some work that was done by Ben, who created a watchdog keyword in Lingua Franca to have the same effect as the watchdog that I just showed you. But we plan to deprecate this and bury it. And
Oh,
as a consequence, I'm not spending any time on it. And the reason is that the federated mechanism and the enclave mechanism that I'll talk about in a minute are both capable of handling this without having any fundamentally new mechanism introduced to lingua franca.
got it, got it.
Okay.
Oh, I have one comment regarding this federated watchdog. I think the early deadline violation detection there can be a little bit conservative because, for example, because of the network delay, basically, because
Right.
watchdog will see the message later than the local reactor with the deadlines sees the event. So
Yes,
yeah.
that's right. But I actually think there's more of a feature than a bug associated
Okay.
with this, right? Which is that if the um, if this monitored process crashes,
Mm-hmm.
okay, the monitor process will still react and will be able to take action because the actuator is not going to be invoked on time.
Mm-hmm.
All right. So the fact that these are separated into two different processes is, I think, an important feature. It actually strengthens the monitoring.
Mm-hmm.
Moreover, because federated execution can be mapped across processors, you can
Right.
put this on two different microprocessors. And so if the whole microprocessor crashes or the whole
Mm-hmm.
network goes down, that's the other thing, of course, is that the network could go down and the actuator might, in fact, be still healthy,
Mm-hmm.
but you might not find out. So
Mm-hmm.
this becomes now a Cal theorem problem, right?
Mm-hmm.
The network latency goes to infinity. You have a consistency availability trade-off. The availability answer is you go ahead and take action in the monitor,
Mm-hmm.
knowing that something has gone wrong,
Mm-hmm.
but you don't know whether it was an
Mm-hmm.
actuator failure or a network failure.
Mm-hmm.
Okay. Or you can emphasize consistency, in which case you can't react, right? So you lose availability. And that's an absolutely fundamental trade-off because of the Cal theorem, right? There's no working around that trade-off.
I see. Okay.
Yeah. But anyway, this ability to separate these into separate processes and separate processors, I think, is potentially a very useful feature. Now, I mentioned earlier that we have a scheduler that tries to do earliest deadline first. And in certain very limited circumstances, it does in fact succeed in doing that. So here's an example where you just have two parallel sensor actuator trains, and the GEDF scheduler does in fact successfully meet the deadlines on the one of these that has low processing time and miss the deadline only on the one that has a high processing deadline. Unfortunately, though, it doesn't work when you have only a single sensor source and you're broadcasting. And the reason is that the GEDF scheduler operates only at the event queue level. And the fact is that there's two distinct timer events on the event queue here, and the GEDF scheduler will prioritize the one with the closer deadline. But here, there's only one event queue event, and it will prioritize it according to the lowest deadline. Okay, but then once it's prioritized it, the level scheduler kicks in and there's no further prioritization in the GEDF scheduler. So the GEDF scheduler really fails to achieve earliest deadline first scheduling. And as a consequence, I propose that we simply retire this scheduler. I think there's really relatively few circumstances in which it actually delivers. And moreover, it underperforms by a significant margin, the default scheduler. And I think the work that Francesco is doing makes it obsolete anyway. Now, enclaves. So Håkan mentioned enclaves. So there is an undocumented mechanism. It's deliberately undocumented because the implementation is incomplete at this point, but it's under development to get the effect of similar to having federates, but where everything is executing in the same process, but you get multiple schedulers that operate independently. And we call these scheduling enclaves. So the syntax, and you can do this in master. So there's an enclaved processor actuator program in this same repo right here. So and it works. Okay, so we can run it, and it will in fact miss a deadline and meet a deadline, and everything's executing in the same process now. But the difference is that when this second processor actuator chain is invoked, it gets labeled as a scheduling enclave. Okay, and what that does is the runtime now creates a separate scheduler for this and runs it in its own collection of threads within the same process. Okay, and then the communication between the two is handled in a manner similar to the centralized coordinator in federated execution. So it'll guarantee that it meets the lingua franca semantics, but now you can have this, because it's in a separate set of threads, you can have it, not interfere. So the excessive execution time of this processor can not interfere with the meeting of the deadline up here. Now, on my laptop, the reason it does not interfere is that I have enough cores. So these will actually execute in parallel on separate cores. If I had only a single core, then I would actually need to prioritize the threads. And that's the work that Francesco is doing, that is ongoing work, okay, where the threads will automatically get priorities based on the schedulers. And so if you don't have enough cores to execute these things in parallel, you will get genuinely earliest deadline first preemptive scheduling. So it might begin executing this long-running processor reaction, for example, and then suspend it because a higher priority thing is kicked in. Okay, so there's work to be done on this, but I think we're really on a pretty good path to getting a really pretty solid real-time system mechanism.